Can you see my screen?
Yes.
Okay, give me 1 second. So today we are going to talk about breadth first search. So what is breadth first search? You are given a graph G equal to V comma E. V are the vertices, E are the edges, and you are given a specific vertex S belonging to V, correct? And you want to know the vertices which are reachable from S, correct? And you want to do this in a breadth first fashion, meaning that what is the procedure you follow? You start from S. Look at the neighbor. So you mark S, correct? Then you mark neighbors of S. Then you mark neighbors of S. And so on, correct? Of course, there'll be, you continue till there is, till no new vertices are marked, correct? And you want to do this in a way so that that you don't explore a node. You do not mark the neighbors of a vertex more than once. So mark the neighbors of correct. So how do we do that? So remember that we have to ensure, we need to ensure that a vertex is explored only once. What do I mean by that? So suppose you have a small graph like 1, 2, 3, 4, 5, correct? And suppose your is 1. So first you would mark S. So you have 1, 2, 3, 4, 5, 5, and this is your mark array. And first you mark 1, then you explore its neighbors, so 2 and 4, correct? So you mark 2 and 4, and then you explore 4's neighbor. Let's say 2's neighbors. 2's neighbors are 1, 3, and 5. 1 is already marked, so you don't do anything. 3 is, now you mark it, and 5 is marked. Now, if you had a way of, if you knew which nodes you had explored, so you have explored this node, you have explored this node, now you explore another marked node, like which was like 4, then you explore 3, then you explore 5, something like this, correct? So you have to have tight procedure in which you want to do this, correct? And the idea is to use the data structure Q. So use Qs to keep track of explored nodes, of yet to be explored nodes. Correct? So, what do you use the Q for? So in this example, let's take this example again. What you do is you have this Q. So you start from S equal to 1. You in Q1, you mark 1. Let me put another mark. So I mark 1, and then I go in the loop. And while there are things to be explored, I take which I find out by looking at the queue. I take out something from the queue. So I take this out from the queue. This is my so this is my currently unexplored node. I explore it by looking at its neighbors, and if they are unmarked, so currently there is no mark here, there is no mark here at 2 and 4. So I in Q2, in Q2, and then I in Q4, and then I mark them, correct? So I mark 2, I mark 4. Now I remove 2. Correct? And I look at its neighbors, 1, 3, and 5. 1 is already marked, so I don't do anything with it. 3, is it marked? No. So I mark it and put it at the back of the queue. And 5, is it marked? No. So I mark it and put it in the queue. And then I take out the next element, 4. All its neighbors are marked, so I just remove it. Then I take out the next element, 3. I look at its neighbors, all of them are marked, so I remove it. Then 5, and so on. So all of them get explored at some point, correct? So is the basic idea clear?
Sir, just to confirm, we are okay with checking whether a node is marked or not multiple times, right?
Yes. Mark is just a bit that you associate with the node, and you can set it to 1, and currently you are just using it to check whether it's already been marked before or not.
Sir, could you repeat that? My internet cut out.
So when you mark a node, when you put a node in the queue, it's an unexplored node, you put it in the queue and mark it. Thereafter, whenever you extract that node, you look at its neighbors which are unmarked and put them in the queue, and so on. So every node gets marked only once, and you can check whether it's been marked before or not. If it's been marked before, that means it has entered the queue. You don't need to put it in the queue again, correct?
Yes, sir. Yeah.
Okay. So, and what is a queue? A queue is a data structure in which you add things from one side and take them out from the other side. So keep on adding on this side and taking them out from this side. Correct? So the two operations supported by a queue are, for want of better names, are append, q.append, and q.extract head.
Sir?
So, tell me.
So in the queue that you've like drawn, you put 4 to the right of 1, right? But it's supposed to go to the left of 1. Is that correct?
No, the 1 was removed. So you're, in some sense, you are correct, but 1 is removed. So the way I should have drawn it was, I put 1 here, then the queue becomes empty, 1 is extracted. Now I put 4 and 2 in the queue. Correct?
Oh, yeah.
I first put 2 and then I put 4. Then I remove this one. So this becomes just 4. And I add back this 3 and 5. Correct?
Yeah.
So this is the state of the queue and so on. So that was not a good drawing. This is not a good drawing. This is what it should have been like. Correct?
Yes.
You said like only a linear data structure, right? It can't have branching.
Linear data structure, yes. It's a yes. it's a linear data structure in the sense that it has two ends. On one side you extract something, and on the other side you append something. Correct? So, is this clear?
Yes, sir.
Okay. Now, so let us write code for BFS. So, def BFS A comma S. Now you might ask, what is A? A is an adjacency matrix, or is the adjacency matrix for G, which means that Aij is equal to 1 if and only if I comma j belongs to G, belongs to E of G, belongs to E. Your G is equal to V comma E. Okay, so it's a matrix and is equal to 0 otherwise.
So,
Let me just say, tell me.
sorry, in the previous thing, I have a doubt. Like when you mark 1 and then you add 2 and 4 and then you mark 2, right? And then you add 3 and 5. Does it
Yes.
matter what you mark next? Like 3 or 4 or 5?
So you are saying at this stage, at which stage? At this stage? One second.
So I can't
At
see.
this stage?
Yeah,
Now
so
can you
after,
see?
no, after that, yeah. After that, you add 3 and 5. And then what do you mark
Yes.
then?
Now there is nothing left to mark.
Oh, okay.
All the nodes are marked. So you will check through the neighbors of 3, 4, 3, and 5, and you will see that all of them are marked.
Yes, sir.
Okay. So, okay. So A is an adjacency matrix for G. Correct. So, firstly we initialize the mark array. So for I is equal to 1. So I will write in range 1 comma. Let me not write in Python code. I'll just write. You can convert it easily to from 1 to n. Do mark j equal to 0. So everything is unmarked. Correct. And your queue is the empty list. It is the empty queue. And now you come to the, you do the initial. So this is the initializations. Now you start the algorithm. So you do mark S is equal to 1. Q dot append S. You add S to the queue. And now, while Q is not equal to empty, what do? You take out an element from Q dot extract head, this thing, and now you check. Now you have to look at the neighbors of V, correct? So for W in 1 to n, if A V comma W equal to 1, and so this means that there is, so, or if you want to write it this way, equal to 1, and mark of W is equal to 0, then what do? So now you know that W is a neighbor of V and it is unmarked. Then you mark W is equal to 1, you mark it, and you do Q dot append W. Correct? Am I making sense?
Yes.
Okay. So this is the basic, the very basic BFS algorithm. Now we will add some bells and whistles to it. For example, we will see how to find connected components and distances and spanning trees and so on, correct? But even before all that, let's run over a simple example. Let's do it here. So how do I do it? So let me take a small example. Something. Let's say this. Okay, just to make sure. Yeah. So now let me give some numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And we'll assume S equal to 1. Okay. So, so now what will happen? So first we have to draw the marked array, the mark array. 1, 2, 3, 4, 5, 6, or let me draw it. Is it not fitting? And I will draw the queue. Yeah, so I will draw the queues here, correct? So initially the queue is empty. Queue is empty. And the marks are all zeros. Correct? So this is at time step 1 in round 1, correct? Then what happens in time step 2? Time step 0. In the first, in the initialization itself, we put this to 1 and put the Q to be S. So instead of S, let me write 1, correct? Are you with me?
Yes, sir.
Now I look at, okay, good. Now I look at all the 10 vertices and see which are the neighbors of 1. So I will go through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I will find that the neighbors are these two. Correct? So, no, even before that, in step 2, I will take out 1 from the queue. I will look at the neighbors of this 2 and 3 and put them in some order in the queue. Let's say 2 and 3. I'm putting on the left side and extracting on the right side. Okay. So 2 and 3, correct? And I mark these 2 and 3 as this thing, correct? Because they were unmarked. So I should have been clearer, but now now I take out 3 from here. So my Q becomes 2, and this thing is 3. And then what are the neighbors of 3? Neighbors of 3 are 1 and 4. 1 and 4. 1 is already marked. So I will. So when I see a 3, 4, it is 1. So it will go inside this. But mark 4 is equal to So when V is 3, when V is 3, Then W and W is 1, then mark 1 will be 1, so this will not be considered. And now I'll go to, from 3, I will go to 4. So I will add 4, and 2 is already at the head. I mean, I will append behind, and 2 remains on the right side. And now what will happen? And 4 will be marked. Correct? Are you with me?
Yes, sir.
Okay. So now I will extract out this 2 so this would become, the Q would become 4 and then 2. And now I will construct the new Q from this. So what are the neighbors of 2? 1, 4, and 5. Correct? 1 is marked, nothing happens. 4 is marked, nothing happens. 5 goes into the queue. On the behind, I append it in the queue, and then I extract. So I had extracted 2, and now I append this 5. So I have drawn the queue in reverse, but it does not matter. Okay. So 5 and 4. And now what happens? Let me draw it here. In the 5th time step, and 5 is marked. Correct? In the 5th time step, I look at the neighbors of 5. I will go through all the vertices, but the things that go through this if statement are only the unmarked neighbors of 5, which are 6 and 7. And 6 and 7 will be marked, and we will put them in some order in the queue. So we would have, we would take out 5. What am I doing? No, sorry, this 5. What am I doing? No, sorry, I missed a step. So here I should go to 4, correct? Please stop me if something is wrong, if something is amiss, correct? So here I take out 4 from this thing, and I'm left with 5, and I am left with 5. I look at neighbors of 4. Neighbors of 4 are 2 and 3, which are already marked, so nothing happens. And then I go to the next time step. I remove 5 from this. This becomes empty. This 5 is taken out, and now the queue becomes, I have populated with the unmarked neighbors, unexplored neighbors of 5, which are 6 and 7. Correct? And so on. This continues. You take out this, and you're left with 6, 7, and now you put in. So I should have 6 and 7 I have marked. Now I put in the neighbors, unmarked neighbors of 7 inside this, which are just 8. So I put 8 and 6. And now in the 8 time step, I will take out 6. And I will be left with 8 in this thing. This has any unmarked neighbors? No, only neighbors are 5 and 8, and they are marked. So, so this is gone. And now I will take out this and be left with empty queue. And what are the neighbors of 8? None. So this is unmarked. Correct? So no, not this is unmarked. So it is removed, and then we are left with the empty queue. And now we are done. Remember, while queue was not empty, we have to do this. Correct? So this 9 and 10 are never visited, and which is correct because 9 and 10 are not reachable from 1. So all the vertices reachable from 1 in this undirected graph is what I have drawn, what I have shown, correct? It was marked, so it is, yeah. Are you with me?
Yes, sir.
Okay, so now you might ask, how do we find all the connected components? What are connected components? Connected components are equivalence classes of vertices which are reachable from each other, correct? Which are connected to each other. So they form equivalence classes, and here 1, 2, 3, 4, 5, 6, 7, 8 are in one equivalence class, 9 and 10 are in another equivalence class, correct? So you have found the first equivalence class. How do you find the second one? So that's simple. You just run this for S in 1 to n, do BFS A comma S, correct? Or you can write this inside a loop and do it multiple times, correct? You might think that this takes a long time to do because you're doing the same thing again and again, but let's do the complexity analysis first. So what is the complexity of this algorithm, of the original algorithm? Let's ignore this for the time being. What is the complexity of this algorithm? Tell me. How would you compute the complexity of this algorithm?
So everything is in the queue exactly once. So we the number of operations I think would be bounded above by the maximum degree of the vertices in the graph times n.
No.
Times the number of
Maximum degree of the graph, yes. So because you are running from the inner loop is from 1 to n, this takes, and all the operations inside are order 1 time, correct? So I claim that the running time of this algorithm is order n squared, as it is described. Is that what you were saying?
I missed one loop, but other than that, yes, I was saying something similar, but I missed one of the loops.
Yeah, so there is while this and for this, correct? There are 2 loops. Everything, like you say, enters the queue exactly once, because or at most once. Here 9 and 10 did not enter the loop, and this loop runs 1 through n, so this is order n squared, correct?
Yes, sir.
Okay. Now you might say that if the graph is sparse, meaning it has something like linear number of edges. If m equal to number of edges is equal to order n, then our algorithm is still running in order n squared time. Correct? Can we make it more efficient than that? Can we give something which depends on m rather than always taking n squared time?
So
So here,
could you repeat the question? Like what do we want it to depend on?
so I'm saying this algorithm takes n squared time irrespective of the number of edges in the graph, correct? Whether you have very few edges or as many as n squared edges, this algorithm will take time which is bounded by order n squared, correct?
Yes.
Because there are 2 loops and yeah, so 2 loops and each loop runs n times, correct?
Yes, sir.
or at most n times. In a connected graph, it will take n squared time, correct? But now we say, what if the graph is sparse, correct? So that is, it has m edges where m is much smaller than n squared. Okay?
Yes.
So m is small o of n squared or whatever, correct? So in that case, can we give a better bound than order n squared? Can we say that this algorithm runs in order m time or order m plus n time? So let's look at the algorithm again. As it stands, there doesn't seem to be any hope, because whatever be the density of the adjacency matrix, you would run these two tight loops, and that would take n squared time. But the observation is that if most of the matrix is filled with zeros, okay, meaning if m is order n, means that only there are on an average of order 1 many ones per row and column, correct? Yeah, n rows and order n elements have 1. Order n edges are there. Excuse me. So there are on an average just constantly many edges incident on a vertex. Do you agree? In a sparse graph, there are few edges incident on a vertex, and therefore looking for the neighbors of a vertex should not, in principle, involve order n time. There are just constantly many neighbors on an average, so it should take time proportional to the number of neighbors. You should not have to, you wouldn't need to go over all the neighbors of all the vertices in the graph in order to find the neighbors of a vertex. So, and this intuition can be made precise by storing the graph as an adjacency list. The answer to this question is yes, and the answer is the search version of this question is that is via the adjacency list representation. Correct? So what is the adjacency list representation? So adjacency list is a list of lists. Okay, the list corresponding to V, so it is a list of lists. The list corresponding to I, the vertex I, correct, is the neighbors, is the number of the neighbors of, is, so this ith list contains the neighbors of I, correct? So if ij belongs to E, then I will put j here. In general, if j1, j2, so on are the neighbors of I, then ij1, ij2, ij3, they all belong to E. Are you with me?
Yes, sir.
Correct? So now how does this help us in running this algorithm in order n plus n time? Notice, so let me copy this algorithm and one second. Sorry. Now for W, I will just change this to say for neighbors W of V, and I will remove this part because these are only neighbors. Correct? And how will I find neighbors? I will just go over the list, the Vth list in this adjacency list representation. Are you with me?
Sir, can you scroll down?
Huh.
Okay. Okay.
So are you with me? Do you agree?
Yeah.
So neighbors W of V can be found by looking at the adjacency list for V, and that contains all the neighbors, and I just have to go over all the neighbors. Okay. So now let's do the complexity analysis of this. So what is the time of the two things? Now there are still two loops, but the inner loop takes how much time?
Constant.
It takes, tell me.
Is it constant time?
Not necessarily. It might not be constant if the degree of V is large. If it has many neighbors, even though the graph is sparse, some of the vertices might have large degree. The average degree is small.
Okay, sir.
Individual degrees could be large. Correct? So the time taken for the inner loop is dv. Correct? Time for inner loop is roughly dv, is order of dv. Correct? Where is equal to dv. So now what is the, each vertex enters the queue only once. So the total time taken, total time is equal to summation of dv plus 1. Why do I write dv plus 1? Because even if the number of neighbors is 0, at least one time is taken, some constant time is taken. Correct?
Sir, so could you, what have you written? You've written time for loop, and then after that you've written something is equal to dv.
I've written time for inner loop
Oh, okay.
is equal to dv, and total time, which is the time for outer loop, which is equal to summation of dv plus 1. Correct? This one is just because even if there are, so this is to take care of isolated vertices. You anyway have to spend one time per vertex, at least one time per vertex. If not for anything else, then to mark the vertices, that will take ordinate time and so on. Correct? So the total time taken is dv plus 1, which is equal to, what is the sum of the degrees of a vertex? Sum of degrees of vertices of a graph?
2 times edges.
Huh? Sorry?
2 times number of edges.
It's twice the number of edges. Correct? Why is it twice the number of edges? Because each edge is counted twice. Every edge u and v, u comma v is counted once from the u side, once from the v side. Correct? So this is equal to order n plus n. Ignoring constants, this is just order n plus n. Correct? So if m is much smaller than n, then this is a definite improvement over order n squared. M is less than n squared, so not n is less than n. For example, n could be linear. In planar graphs, it is linear, and so on. Correct? Many classes of graphs. Yeah. So, so this is called linear complexity. Why is it called linear complexity? Because it is linear in the number of vertices and edges in the input representation. Correct? So, if you compare adjacency list and adjacency matrix, and so there you process time for time to process neighbors is order n here, and here it is order d of v. Correct? And on the other hand, there is a flip side to this also. To find whether ij belongs to E, this test takes order 1 time here, but it still takes order dv time here, because you have to go through the entire list to see whether ij is there or not. So v comma w belongs to E. Yeah. Correct? Are you with me?
Yes.
Okay. Okay. So let's add let's add some bells and whistles to this thing. One question is, how do you identify the components of the connected components of a graph? So for example, we had this graph. We said we would do this. Run this BFS algorithm n times. So now what is the complexity of this algorithm? Suppose you do it with adjacency list. What is the complexity of this? Tell me.
O of n times m plus n.
That is certainly an upper bound, but is it the best upper bound you can? I claim this algorithm also takes this. Why is that so?
So could you repeat the claim? I couldn't hear you.
So the claim is that this algorithm, it's not of much use, but we will make it useful in a second. So this algorithm, what is the complexity of it? Someone had claimed that it is, naively speaking, it is n times m plus n, but it is also equal to order m plus n. This is a better bound. Why is that so? Because of the marked thing, you would never visit. So even though you run this n times, marked vertices will only be visited once. A vertex will be marked only once, correct? So here I assume that this mark is a global array. So, do you see my point? It's not local to BFS. I do it outside.
Yes, sir. I think I see now.
Yeah. So I will just move it outside, and now it is. Now this will run in order n plus n time. Do people see that? Is there any confusion about this?
So I'm not sure.
Okay. Okay. Good. Good that you asked. So, so firstly, this should be I, j, mark I equal to 0. So for j in 1 through n, do mark I equal to 0. You unmark all the vertices once. Then you run this algorithm. For s in 1 through n, do BFS a comma s. So remember, there is this for I equal to 1 to n, mark I equal to 0. This is implicitly outside. And then I run this BFS algorithm, which BFS function. So I claim that a vertex will be visited exactly once in this. A vertex will be marked only once and it will be explored, meaning, so I am now doing this one for neighbors W of V. It will be explored only once, correct? Because it has been put in the queue only once. Those vertices will be explored only once. That might happen during different iterations of BFS, but nevertheless, it will happen only once.
Okay, yes, sir. I see it now.
Correct?
Yes, sir. Yes, sir. Thank you, sir.
Okay. 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 So therefore, this also runs in order n plus n. But what is the use? Now this everything will be marked. But now you can say that instead of marking it with 1, let's say, so this again I should move outside. Let's say I mark it, so this I move outside, and what I do is I mark these with S, with the mark S equal to S and mark W equal to S. Correct? So the mark that I put on the vertices is S. Now what earthly use is this? The use is that you will get all the vertices with the same mark will all the vertices with the same mark will be in the same connected component. Do you see that? So, and things with different marks will be in different connected components. Another way to do this is to, let me alter the definition of BFS. 1 second. Let me change this and put a different marker altogether. Different mark altogether, which is the number of the let's say we put AS comma B. Okay. So I will put mark W is equal to B, and also mark S is equal to B. And now in the loop, in the main program, I will write is equal to 1 to N do mark I is equal to 0, and then I do for I is equal to 1 to N do, or for S is equal to 1 to N do for uniformity, BFS, and I initialize C is equal or B is equal to let's say 1, correct? Or B equal to 0, let's say. B is equal to B plus 1 or whatever. Yeah, B is equal to B plus 1, BFS, A comma S comma B. Now what will happen? Now can someone tell me what will happen?
Sir, a small thing. I guess in our BFS now, before marking S, we should check if it's already marked. Otherwise, we might mark, like we might go over connected components multiple times. Because I don't think we're
But we are
skipping.
checking that, huh? We are checking this mark W equal to 0, correct? No, where do we want to check?
In BFS before marking S. So in between the second and third lines.
Oh, okay. Yes. So, okay. So, I mean, that will not affect the correctness, but you are correct. If mark S equal to 0, B is equal to B plus 1, correct? Sorry. Correct. So every time you check whether a vertex is marked, if it's unmarked, then you increment B and then you do BFS with this count B. Correct? Are you with me? Do you see? So the first component will be initialized to the first component, the marks will be 1. In the second component, the marks will be 2. In the third component, the marks will be 3, and so on. Correct? Do you agree with me?
Yes, sir.
Okay. Now, you might also say, so let's go back to the initial definition or initial intuition behind breadth first search. We said we would mark S, then mark the neighbors of S, then mark the neighbors of S, and so on. So in some sense, we are saying that we are exploring things in kind of ring-like fashion, correct? All things at distance 0 are explored first. That just consists of the vertex S. Then those at distance 1, and those at distance 2, and so on. So this is the intuitive notion of distance that we have in mind, correct? Things are explored in terms of their distance from S. Can we make this intuition precise? So how do we make sure that we mark the distance of a vertex from S. So let's copy the first algorithm. I mean the algorithm after. I think I changed it here only. It's not good, but yeah, fine. So let me copy this one. Is the objective clear?
Sir, then there will be two numbers for each mark.
Now there will be something called distance. That's
okay.
what we mean. Correct? So we will say for I, the initialization will remain same, but I0 1 to n mark I equal to 0 and distance of I is equal to a very large number which we'll call infinity. Okay, which is larger than n, say n plus 1. Correct? And let me revert back to one here. So now you want to find the distances from this thing. So how do I mark distances? I will remove this part, of course. Tell me. So the distance, I will just say distance of W is equal to distance of V plus 1. And here I make distance of S equal to 0. And I claim now at the end of this, the D array will be populated with the distances from S, which are finite if S is reachable, if that vertex is reachable from S, and they are infinite if it's not reachable. You see why?
No, sir.
Huh? Sorry, I couldn't hear you.
Sir, is dv is infinity, right, in the beginning?
dv is infinity in the beginning. ds is 0. So,
okay.
And you increment it by 1 when basically you mark W, correct? So S's neighbors will get a distance of 1, 0 plus 1. S's neighbors will get distance which is so the short will be 2 and so on. So the shortest path from S to a vertex, so dV will be equal to the length of the shortest S comma V path. And by length, I mean equal to number of edges on the shortest S comma V path. Correct? So S to S, there is no edge, its distance is 0. S to its neighbors, there's one edge, the distance is 1, and so on. Correct? Are you with me?
Yes, sir.
Okay. Now, another thing which you can do is to somehow associate. So suppose you want to construct a tree, which is the shortest path tree. So any path, shortest path tree from S. So you want to find the shortest path from S, find the shortest path from S to any vertex. How will you do that? Or from any vertex to S. Currently we are talking about undirected graphs, but this algorithm will work for directed graphs also. I invite you to check that. We have implicitly assumed that the graph is undirected, but even if it is directed, the exact same algorithm will work. But so in undirected graphs, how will you find the shortest path from S to any vertex? Tell me. The
shortest
path
suppose we want to find shortest from path from S to a neighbor, then we will just append that S, and then again for again neighbor we will go to the previous D of name shortest path of V, including V. D shortest.
So what you're saying is we'll create another array, correct? Say call it the parent array. Parent I is equal to, let's say, -1. And let's say parent of, or let's say, remove this, correct? And here we just put parent of, we just link parent of W is equal to V. Correct? So the shortest path to W goes via V. There might be many paths, one of them goes via V. Do you see my point? So now by tracing these pointers back, you can get the shortest path from V to S and therefore from S to V. So what is the shortest path from? So that will just be parent of V, comma parent of V, comma parent of V, and so on till S, till you reach S. Correct? Do you agree to this?
Yes, sir.
Okay. Moreover, this is the shortest path, therefore cannot enclose a cycle.
Sir?
Tell me.
So this is for any general graph, right? Like where we're looking at the shortest path and then making them parallel.
Yes.
It's not for a tree. I mean, I think you said tree somewhere in the middle. I don't understand.
Okay. Yeah. So what I'm saying is, if you look at this another graph, which is formed by, which has edges V comma parent of V, correct? So
Yes.
this is a subset of the edges, correct?
Yeah.
This forms a tree. S doesn't have a parent, of course. We never change the parent of S from -1. So all other things reachable from S have parents, and this graph is a tree. And while I will not give a proof of this, if you think about this graph, where did that graph go? This graph. Let's look at this graph, detail. So here, while we were exploring this graph, we were putting parent pointers also, suppose. Then we would put a pointer from 2 to 1 and from 3 to 1. And then we would explore 2 and we would put a pointer from 4 to 2 and 5 to 2. And similarly, we would put a pointer from here and here. And then we explored this, so we put a pointer like this. Now observe that the directed edges that I have drawn forms, if you ignore the directions on those edges, it forms a tree. Do you agree with me?
Yes.
This is a undirected tree. It's also 9 and 10 do not have any edges in this because they are not reachable from S. But this is a directed tree rooted at S. All the edges are incoming to S. If you draw the directions, they are incoming towards S, correct? Moreover, the edges that got left out, what is their structure? So let me draw them as directed, as dotted edges. These are the edges which are left out, correct? So in the part that is reachable from S, they form cross edges. So these are non-tree edges which are cross edges. What do I mean by cross edges? By cross edge, I mean that if you look at look at this edge. A cross edge is a non-tree edge such that neither of its endpoints is an ancestor of the other in the tree. If you come on, there is no directed path from U to V or from V to U in the directed tree. Are you with me?
Yes, sir.
Okay. So for example, this is UV. There is a there is no directed path from U to V because there is an edge against this. In the unique tree path from U to V, one edge goes against it, and similarly from V to U, there is no path because these two edges go against it. Correct? This is called a cross edge. You could imagine that there could have been an edge like this. Correct? Suppose this were a tree. This is not a cross edge. This is a back edge or a forward edge, whatever. Its endpoints are comparable. There is a path from here to here, and such edges do not arise non-cross edges that are non-tree edges that are also non-tree edges with respect to a BFS tree do not exist. Are you with me? Such edges do not exist. Can you tell me why? Can someone tell me why such edges do not exist?
Vertex, the BFS would add that edge first.
Yes, that's one way of seeing it. The other way of seeing it is that the distance, suppose this edge is UV, correct? Then what is DU and what is DV? DU and DV differ by more than 1. Correct? And this cannot occur. This, why can't it occur? For the reason that you just said, that at this point you would have been explored first. I mean, this is not a shortest path from S to U. In this case, there's a shorter path from V directly to U, so that would have been explored first. Correct? Do you agree?
Could you repeat? I don't think I understood the last bit.
So what I'm saying is, if you believe me that the shortest paths, that this tree captures shortest paths from S to every vertex, correct? Do you believe that?
Yes, sir.
If you believe that, then look at the shortest paths from S, the purported shortest paths from S to U. Correct? It goes via this tree. That's what the claim is. But there's a shorter path which takes this edge to U. Because this path is length at least 2. V is not the parent of U. V is some ancestor of U. So it is this path from V to U is at least of length 2, while there's a direct edge between them. So there's a way to short circuit the path via V, come to V from S, and then go to U. This path is shorter than the tree path.
Yeah, yeah.
That would contradict that this tree is the shortest path. So therefore, non-cross edges that are non-tree edges do not exist in a BFS tree with respect to a BFS tree. One last thing I want to say is, how will you, this is a very simple property and I guess all of you can see that. How will you find whether a graph is not a tree? Or how will you find whether a graph has a cycle? An undirected graph has a cycle. How will you detect that? How will you
An edge will
detect?
occur more than once.
Edge occurs more than once? Detect,
In the loop.
yes, but there's a simpler way to do that.
So it has at least n edges.
Okay, that's another way of doing it. But the most direct way, and if you were to find a cycle, how would you find such a cycle? Just do BFS and look at a non-tree edge. Look at a non-tree edge. This along with the tree path will give you a cycle. This is a cycle. Similarly, this is a cycle. Correct? Do you see my point?
Yes, sir.
Every non-tree edge with respect to a tree witnesses that the graph is not a cycle. Is not a cycle. It has a cycle. Correct? And this n-1 thing will only work if the graph is connected. Correct? So for example, if you have 4 vertices and 4 edges, then the graph has a cycle. Correct? But if you have 5 vertices, then there are 4 edges, and this does not tell you that the graph is acyclic. Do you agree with me?
Yes, sir. No, but if it has at least 5 edges, then it will have a cycle.
No. You said there are n-1 edges. If it has n edges, it has a cycle. Correct? That is true. But this graph does not have n edges. It has n-1 edges and yet has a cycle.
Oh, yeah, yes.
So your thing was sufficient, but it's not necessary and sufficient. Correct?
Yes.
Okay. Any questions about today?
Sir, can you take the naive algorithm? The first one that you
Sorry?
did. The first, can you take
Huh.
the first algorithm? So the
This
one where we check for all vertices.
Huh.
So will that be order n square for if we check for all vertices too?
If we run this under this loop, you're saying this one?
Yeah.
No, then it will not be. Then there'll be 3 loops and it will run in order n cube time.
Sir, so if it's marked once, then it won't enter the queue, right?
No, it will still enter the queue. It will still enter it. Huh? You would still, for W in 1 through n, so this would still be n squared and each iteration would be n squared. So though you save only when you do not enter, basically it will be order n cube. You are correct. I mean, this is order m plus n or order n cube depending on matrix versus list. Huh. Okay, tell me, can you see why it will be order n cube when it's a matrix?
Yes, I think I understand. The loop will be executed. Yeah, it won't be. It will be checked for whether it's marked or not. Yeah. Yes, sir.
So that's a good point. And moreover, I should have said this not BFS A comma S, but list comma S or something. So now we are doing it with that C list. So you understand, no?
Yes, sir.
Okay. Okay. So more questions? I should remove this A from here and put a list L. A, L. Yeah. More questions? If not, then let's conclude today's lecture and we meet again on Thursday. And soon there'll be a quiz, probably next week. Correct? Okay, thanks. Bye.
Thank you,
Thank
sir.
you, sir.
Thank you.
Thank you.